Welcome to Ask and Learn.
So for this problem, we're going to let AS1 and AS2 represent the areas of the cross sections of the solids S1 and S2. So the volume of S1 will be equal to the integral of our bounds A1 to B1 of AS1 dx. And similarly, we have our volume of the S2, which is A2 to B2, AS2 dx. So based on this, we're assuming that AS1 equals AS2. Because the planes of the cross sections are parallel, we know that the bounds of the integrals are equal. So A1 equals A2 and B1 equals B2. So based on this, since these two areas are equal to each other, and then we also have that the bounds are equal to each other, we can conclude that A1, B1, AS1 dx is equal to A2, B2, AS2 dx. So what that ultimately means is that VS1 is equal to VS2. Then for part B, we have a given cylinder C1, and then we have another cylinder C2 with height h and radius r. And we can assume that their lower bases are in the same plane. Using the principle that we just discussed, what we have is that the volume of the first one equals the integral from 0 to h of a1x dx, and that's going to be equal to r squared pi times the integral from 0 to h dx, and that's just r squared h. Then what we also do is V2, and we end up getting that this is going to give us the same result of r squared pi h. And we already knew that their bounds were equal, so we see that since their volumes are equal, we can set up those cylinders on the same plane, and it's clear that they have the same intersection with corresponding plane, and we see that their volumes are equal, which is what we wanted to show. And this is r squared pi h, by the way.